Hi everyone. Today we're going to finish up our discussion on solutions. So we're actually going to skip colloids for this chapter. However, if you are interested in that topic, you can read more about it in your textbook, or I'll also post the slides for that information. But I'm not going to test you on colloids. So today we're going to focus on solution properties. Now, one interesting thing about solutions, some solutions can conduct electricity. In those solutions, we'll have ions that are positively and negatively charged. And if we put two electrodes into that solution, then the positive ions will actually be attracted to a negatively charged electrode, and the negative ions will be attracted to the positively charged electrode. And then because we'll have a flow of ions, that's going to generate a flow of current, which can produce electricity. So pure water, just on its own, conducts electricity very poorly. Now, if we write out a reaction between two water molecules, we do produce two ions, but they're going to be produced to a very small extent. So these two ions won't produce a current, really. Maybe a tiny one, but not a significant one. However, if we have a solution of, for instance, sodium chloride, NaCl is going to dissociate into sodium ions and chloride ions in solution. And this dissociates really well in solution. So up above we have a really small amount of ions coming from water reacting with itself. But with sodium chloride, we have a large amount of ions in solution. And of course, this will be concentration dependent too. So the more sodium chloride that's dissolved, the more sodium and chloride ions that will be produced in solution. So if we have a solute that can dissociate into ions, we call those electrolytes. And you might have heard of electrolytes in Gatorade commercials. So Gatorade actually has a lot of sodium and potassium ions. And those ions are particularly important for cell function and also for brain function as well. So if we have a lot of electrolytes in solution, and then let's say we put two electrodes into that solution, and let's say one electrode is positively charged and one is negatively charged, the positive electrode will attract the negative ions, and the negative electrode will attract the positive ions. Now, whenever we have a flow of ions or ions that are moving around, that generates a current. So if those electrodes are connected to a battery that's connected to a light bulb, we can generate electricity and that light bulb will light up. All right, now some solutes do not dissociate, in water. So for instance, sugar, which is C12H22O11, that stays exactly the same in water. It does dissolve in water because it is a polar molecule, but it does not dissociate into ions. So that would be considered a non-electrolyte, and it's not going to produce a current just due to the fact that it doesn't produce ions in solution. So an example of that is shown over here, where this would be a non-electrolytic solution. Now in the middle here, we have a weak electrolyte. So some electrolytes can generate a current, but they might not generate a very strong current. So there are a wide range of electrolytes that exist. Okay, so just to summarize again, strong electrolytes form solutions that conduct electricity because they dissociate completely into charged ions when they dissolve. And then weak electrolytes form weakly conducting solutions because they dissociate into ions only slightly when they dissolve. And then non-electrolytes form non-conducting solutions because they do not dissociate into ions at all when they dissolve. So again, a strong electrolyte would be something like sodium chloride. A weak electrolyte, one example would be hydrofluoric acid. This is called a weak acid. So it only dissociates slightly in solution. And we'll talk more about acids in the future. And then non-electrolytes would be something like sugar. So C12H22O11. All right. So another set of properties for solutions are colligative properties. Colligative solution properties are properties that depend only on the concentration of solute particles in the solution. So these are concentration dependent properties. So three colligative properties are boiling point, freezing point, and osmotic pressure. So remember from earlier in this chapter, we talked about boiling point and how that depends on vapor pressure above the liquid. So what's interesting is if we measure the vapor pressure of pure water versus the vapor pressure of a solution, the vapor pressure above a solution is much lower than the vapor pressure of pure water. So above water here, we have a higher vapor pressure. But in a solution, which is a mixture of solute and solvent, we have a lower vapor pressure. So there's less gas above the liquid. Now, the reason for that are these solute particles. They're kind of blocking the water from being able to escape or evaporate. So the solute is lowering the vapor pressure, or it's decreasing the ability of the water to evaporate or turn into a gas. Now that's important because it's going to have an effect on the boiling point of that solution. So the boiling point of a solution is always higher than the boiling point of the pure solvent. So let's say that we have pure water and we have a sodium chloride solution. So let's say we have NaCl in that second beaker. If we start heating both of the beakers at the same time, the water will start boiling first. So water will boil at 100 degrees Celsius. But remember, we need the vapor pressure to match atmospheric pressure in order for a solution to boil. So in the solution, because we're not getting high enough vapor pressure, it's going to take more heat or more energy in order to get to that appropriate vapor pressure. So for the solution, we need a higher temperature in order to get to the same vapor pressure. So what that means is the boiling point of a solution will always be higher than that of pure water. It might not be much higher, but it will definitely be greater. And again, that's because we need a higher temperature in order to get the same vapor pressure that matches atmospheric pressure. And again, that's due to all of these solute particles that are blocking the water from evaporating. All right, so there is an equation we can use to determine the change in boiling point for a solution versus a pure solvent. So the difference between the boiling point of the pure solvent and the solution is represented by the symbol delta TB. So that's the change in boiling point. And again, we're comparing the pure solvent to the solution. So the difference in boiling point between pure solvent and solution depends on the concentration of solute particles. So delta TB is equal to a value N, a constant Kb, and the concentration M. All right. So again, delta TB is the difference between the boiling point of the solution and the boiling point of the pure solvent. So delta TB is actually going to be a pretty small number, so something like maybe 0.5 degrees Celsius or 1 degree Celsius typically. But again, that's just the difference between the boiling points. So let's talk a little bit more about each of those different variables in the equation above. What is N? What is Kb? And then M is molarity, so that's moles per liter. Okay, so let's talk about N. N in the equation is the number of moles of solute particles that are put into solution when 1 mole of solute dissolves. So, for instance, solutes that do not dissociate have an N value equal to 1. So we said in a previous slide that sugar does not dissociate in solution. So if we add it to water, it goes from a solid to aqueous. But it does not turn into ions. So N equals 1 because there's only one product. Now, if we have something like sodium chloride, which does dissociate completely in water, we have sodium ions, which are now aqueous, and chloride ions, which are now aqueous. So we have 2 products, so N is equal to 2. So this value of N, we did say previously in the gas equations that it was equal to the number of moles. And here it kind of is too. We're kind of adding up the number of moles of product. But again, N is the number of moles of solute particles that are in the solution after they dissolve. Another example, let's say that calcium chloride is dissolved in water. So when calcium chloride dissolves, we end up with a calcium ion and 2 chloride ions because we have a 2 here next to chlorine. So we end up with 2 chloride ions. So when 1 mole of calcium chloride dissolves, 3 moles of ions are put into the solution. So N would equal 3. Now, Kb in the equation is a constant called the boiling point constant. So Kb is just something that you look up in a table, basically. So this is something that's typically measured for us or determined for us. So you'll usually be given the value of Kb in a problem, or you might be asked to solve for Kb and you'll be given all of the other components that you need. And then M, again, is the molarity concentration of solute in the solution. And that's in moles per liter. All right, and let's do a practice problem. So we'll actually use our equation where delta TB is equal to the moles of ions in solution, and times the boiling point constant, Kb, times the concentration, capital M. So let's say we have a solution of sodium chloride, so it's dissolved in water, and that solution has a boiling point of 101.4 degrees Celsius. If the boiling point constant for water is 0.52 degrees Celsius per molarity, then what is the concentration of this solution? Okay, now remember, we're always comparing the solution to the original pure solvent. So in this case, the pure solvent is water. So let's write out a couple of variables here. So the boiling point of the pure solvent, which is just water, is equal to 100 degrees Celsius. And that's always true for water, at least at sea level. We talked about how that can change as you go higher in elevation, but for now we'll assume we're at sea level. And then the boiling point of the solution, we were told, is 101.4 degrees Celsius. And then we're told that Kb is equal to 0.52 degrees Celsius per molarity. Now we have to figure out what N is. And earlier we said that when sodium chloride dissolves in water, we end up with sodium ions and chloride ions. So we have 2 ions as our products, so N will equal 2. And then we're just going to solve for the concentration M. All right, so let's plug everything in. So the first thing we need to do is take the difference in those 2 boiling points so we can get delta TB. So delta TB will equal 101.4 degrees Celsius minus 100 degrees Celsius. So that's equal to 1.4 degrees Celsius. So now we can set that equal to N, which is 2, times Kb, which is 0.52 degrees Celsius per molarity, and then we have M. So now we just need to rearrange this equation to solve for M. So M is equal to 1.4 degrees Celsius divided by 2 times 0.52 degrees Celsius per M. So if we cancel units here, degrees Celsius cancels, and then we're left with molarity, which is in the denominator of a denominator. So that's going to actually be in the numerator. So if we take 1.4 and divide that by 2 times 0.52, we should get a value of 1.35 moles per liter. So that is the concentration of our solution. Okay. Now, we also said that the freezing point depends on the concentration of a solution. So the freezing point of a solution is always lower than the freezing point of the pure solvent of the solution. So we have a pure solvent on the left, and if this is water, we know that water is a polar molecule. So water molecules will be attracted to each other through hydrogen bonding. So water is going to always freeze at 0 degrees Celsius. However, let's say we add salt to water. So let's say we put some sodium chloride in there. The ions in solution from sodium chloride are going to prevent the water molecules from being attracted to each other because the sodium chloride ions will kind of be in the middle of some of the water molecules. So that's going to prevent the water molecules from forming a crystal at 0 degrees Celsius. Instead, we have to decrease the temperature past 0 degrees Celsius in order for freezing to occur. So we lower the freezing point. So again, the freezing point of a solution is always lower than the freezing point, just due to those extra solutes. Now this is actually really useful because, for instance, in the winter, if you want to prevent ice from forming on your driveway or your sidewalk, you might put some salt down on your sidewalks. And that's because water will freeze at a much lower temperature if it's mixed with salt. So the salt prevents the water from forming crystals. Now, of course, if it gets cold enough, then there's not much you can do, but you could always add more salt and raise the concentration. Of course, then that adds to the deterioration of things like pavement, etc. But anyway, you get the idea. All right, now for the change in freezing point, this is very similar to the change in boiling point equation. We're going to use delta TF to represent the difference in freezing point of the solution and the pure solvent. And that's calculated by subtracting the freezing point of the solution from the freezing point of the pure solvent. So delta TF would equal the freezing point of the pure solvent and the freezing point of the solution. So we're taking the difference between those two. And we should get a positive value for that. All right, and then the equation down below tells us that delta TF is equal to, again, N times the freezing point constant times the concentration of the solution. So again, Kf is a constant that you would either be given or you would solve for. Now, the last colligative property, so the last property that depends on concentration, is osmotic pressure. So if you are interested in biology, osmotic pressure is really important in our cells. So there is solution going across our cells constantly and our cell membranes. And if the pressure inside of our cells is too high, that can cause our cells to burst. If the pressure within our cells is too low, that can also be bad. We always want to maintain a pretty consistent pressure. And this has to do with something called osmosis. So when solutions that have different concentrations of solute are separated by a semi-permeable membrane, solvent will flow through the membrane in both directions. So this is very similar to a cell. So if we have a cell membrane, which is semi-permeable, so that means things can sort of pass through it, but it depends on their size. So small particles can maybe pass through, but not large particles. Um, so water, for instance, can pass back and forth across a cell membrane. However, let's say there's different concentrations of solution on either side of that membrane. Then solvent is going to flow from the less concentrated solution into the more concentrated solution, and that's called osmosis. So for instance, let's say that we have a lower concentration of solution inside of a cell. And let's say there's a pretty high concentration of solute outside of the cell. So again, solvent's going to flow from the less concentrated area to the more concentrated area. Now that could decrease the pressure inside of the cell, which could be bad for the blood cell or other types of cells. Now, if the situation is reversed, so let's say we have a cell and there's a high concentration of solute in the cell and a low concentration of solute outside of the cell, then water's going to flow from the low concentration area to the high concentration area. And that could increase the pressure of inside of the cell, which could cause it to burst. So we always want to maintain an appropriate concentration inside and outside of our cells. All right. Now, there is a way to stop the flow of solvent. So when the more concentrated solution involved in osmosis is put under sufficient pressure, then we can stop the flow of solvent. So let's look at another figure to kind of see how this works. All right, so on the left we have an initial state where pure water is on one side of a semi-permeable membrane, and then a sugar solution is on the opposite side. Now, remember, if you have more solute, that's going to increase the concentration. So the right side of this beaker has a higher concentration of solute. So that means solvent is going to naturally flow over to that side. So systems typically want to act in a way where we're diluting something that's at higher concentration. So that's osmosis. All right, so eventually we'll reach a point where water stops flowing because we've reached our osmotic pressure. However, let's say we don't want solution to flow to the other side. Then maybe we'd want to set up a system where we place pressure or like a lid or something on top of the sugar solution. So we're going to place some pressure on top of that solution. That's going to prevent the flow of solvent. We could even push that lid down further and push solvent back over to the other side. So, however, on the right-hand side, we can see that the amount of solvent on the right-hand side has increased. Now, this difference in height actually correlates with what's called that osmotic pressure. That's the amount of pressure we would have to exert in order for solution to not change. Okay. Now, the pressure necessary to prevent osmotic flow of solvent is called the osmotic pressure of the solution. Now, that's represented by a symbol pi right here. And there's also another mathematical equation we can use to determine that pressure. So that's equal to N, which is the same as the N value we saw before for boiling point and freezing point. And then that's multiplied by concentration in moles per liter. And then we can also multiply that by a gas constant. And then we multiply that by temperature. So in this particular equation, they're using a gas constant that's equal to 62.4 liters times torr per mole Kelvin. And then temperature has to be in Kelvin again. All right. Now there's one more definition here. So if we multiply N times M, that's called the osmolarity of the solution. So this is all information that's actually really important in for our bodies again. So osmotic pressure can have applications in all sorts of areas of the health industry. All right, so I think that's the end of chapter 7. Again, if you're interested in colloids, which are homogeneous mixtures of two or more components, feel free to read more about them. I'll include the slides on Canvas. However, just in the interest of time, we're going to go on to the next chapter. So I will see you then.